One term that best describes the all-around capabilities of the McCracken Vibromac die-cast machine, it's probably versatility. This applies not only to the wide variety of products and shapes that this machine can make, but also to the way it can be adapted to various plant situations and customer specifications. Vibromac versatility took on yet another dimension recently when 132-inch diameter pipe produced on the machine were jacked underneath a New Jersey river channel using a unique tunneling method making its first appearance in the United States. Successful bidder to supply the pipe for this large tunnel project was New Holland Newcrete Products of New Holland, Pennsylvania. During its bid preparation, New Holland Newcrete contacted McCracken's engineering department to see if it was feasible to manufacture the massive 132-inch by 10-foot long sections, each with a 15 5/8-inch wall thickness on the company's existing Vibromac machine. McCracken assured New Holland that the machine was equal to the task, and the result was a combined effort between the two companies on equipment and joint design to produce a piece of pipe that would meet the project's stringent tolerances and design specifications. In particular, the challenge of the job inspired a new concept in Vibromac formwork, as the finished pipe would weigh 40 tons each and would be the heaviest single pieces ever produced on any McCracken machine. New Holland's bid was ultimately accepted, and upon delivery of their new 132-inch Vibromac equipment, production commenced on the 351 pieces of pipe needed for the job. Cage design and construction was an initial manufacturing concern, and a special reinforcing scheme was devised using epoxy-coated spacers, stirrups, and stirrup retention rods. Reinforcing consisted of a double-wrapped inside cage and a single wire mesh outside cage. In excess of 3,800 stirrups were placed between the inner and outer cages, and they were locked into position by 64 retention rods. Besides giving each piece of pipe the normal load-carrying capacity, the reinforcement was also designed to help the pipe withstand the powerful jacking forces on the upcoming tunnel job. Once fully assembled, each cage weighed over 2 tons. The final assembly process began with the placement of a special steel bell ring on each machined bell pallet. Retention anchors welded to the steel bell ring would secure it into the wall of the cured pipe. This steel banded joint assured joint flexibility and integrity, as well as gasket containment. Once the cage assembly was set on the pallet, 2 lifting inserts were placed in the walls for the handling of the finished product. The core was then lowered into the assembly, and the entire setup carried to the pipe machine with an overhead crane. With the placement of the tongue former, production commenced. New Holland's Vibromac turned out an average of 5 pieces of the 132-inch diameter pipe per day, with each manufacturing cycle lasting between 50 and 60 minutes. The type of installation viewed here illustrates yet another facet of Vibromac versatility, as the machine may be installed in a pit, such as this one, in a partial pit, or at floor level. The choice belongs to the producer. During the manufacturing cycle, material was vibrated to consolidate the concrete around the reinforcing into a dense, smooth wall, which formed the barrel of the pipe. In this instance, the 132-inch by 10-foot form was fitted with 16 vibrator mounts for the MCD 3 5400 electric vibrators. When the mold was full, a pusher plate was used for final spigot formation. Then McCracken's patented cap positioner assemblies, here using length compensating blocks, hydraulically forced the plate into the concrete for maximum compaction of the spigot or tongue end of the pipe. Upon completion of this process, the pipe and core were stripped from the form using the overhead bridge crane and the Vibromac's hydraulic core lift cylinder located in the machine pit. As each pipe was removed, the barrel was wrapped with a plastic film. This helped retain the moisture in the barrel, ultimately providing for a more complete hydration of the cement to produce higher ultimate concrete strengths. Each piece was then transported to the curing area where it was set down, the pallet retainer lugs retracted, and the core removed. At the end of the production day, the pipe were covered so the 12-hour curing cycle of misting and steaming at elevated temperatures could take place. The following morning, after the curing kiln cover was rolled back, the tongue formers were removed. The lifting gear was then attached and the pipe were raised from the bell pallets and rotated 180 degrees so they could be stored on the spigot ends. The pieces were placed in this flower pot position so the steel joint rings on the bell ends would not be disturbed. Before being taken from the curing area, each pipe was tested with an OD gauge to ensure that it would fit through the eye wall of the tunnel. A lowboy trailer next carried the pipe to the finishing and testing area of New Holland's plant where the joints were dressed. When this was completed, a rubber joint seal was placed on the tongue end and each piece was tested to 10 psi to assure joint integrity. For final joint preparation, a 12-segment wooden packer was secured in the bell end with an adhesive caulking material. This packer was later utilized to cushion and equalize distribution of the jacking forces during installation. It also served to retain the specially designed 1 3/8-inch square rubber gasket that was inserted to both seal and cushion the joint during pipe laying. The finished pieces were then yarded. When shipment was requested by the job's general contractor, Load-A-Johnny USA, the contract hauler was able to deliver 4 to 6 loads to the job site daily, one 40-ton piece per load. Before leaving New Holland's yard, a rollover gasket was placed on the spigot end of each pipe and secured with a plastic wrap to hold the gasket in position during transit. Special permits and escorts were required for the 156-mile trip to the New Jersey job site. And what a sight it was, along the banks of the Raritan River near Sayreville, New Jersey. The job concept called for the construction of a new outfall line from an existing sewage treatment plant to a target shaft located on an island in the river. Part of the completed tunnel would have to drop beneath the shallow 1,700-foot wide south channel of the river to connect with the target shaft. Once the job was underway, the 132-inch pipe sections were lowered into the tunnel access shaft and installed in pairs. Jacking power was supplied by a thrust ring using 8-foot-long primary thrust jacks capable of providing a force of 5.4 million pounds. A thrust ring spacer was also used to extend the efficiency of the jacks. In general, this system, with its unique HydroShield tunnel boring machine, is capable of jacking up to 12 feet per hour. Due to project site conditions, however, the tunnel's subcontractor, Hawkteeth, could average only between 2 to 4 feet per hour. The crews kept the work going 24 hours a day, 6 days a week. At the head of the tunnel, excavating the shaft into which the pipe were jacked, was the HydroShield tunnel boring machine attached to the first pipe section. Located directly behind the HydroShield was the computerized operation center, where a driver continuously monitored and steered the shield to maintain proper course and alignment. Spaced along the entire length of the tunnel were 9 intermediate jacking stations with 32 local force jacks per station to aid in the push. The tunnel was also equipped with a piping system for the bentonite lubrication to the cutter head chamber and for the conveyance of excavated material in a slurry form. The completed tunnel measured 3,450 feet in length, and it was installed with a curved alignment section with a 3,100-foot radius. Maximum cover on the tunnel was 60 feet below ground level, and maximum water level was 40 feet above the tunnel's crown. The target shaft was a cofferdam on an island in the Raritan River, where a connection was made with a marine outfall diffuser. The concept for the Sayreville Supplementary Outfall Project had originally called for an open trench installation. This idea was ultimately rejected because of concerns for the environment. The choice then went to a concrete tunnel alternative, since underground jacking would not disturb either existing physical structures or the surrounding terrain. The resulting tunnel marked the largest and longest jacking job of this type in the United States, and it was also the first use of the HydroShield tunneling method in this country. McCracken was pleased to have been one of the participants in a job of this scope and uniqueness. Through a massive joint effort by all parties involved, the task was carried to its successful conclusion. The tunnel was more than a vision. It was a lot of hard work, but we made it to the end.